Hey guys, welcome to the third calculus lesson. This one's going to be on continuity, which was briefly touched on in the very first lesson where I talked about left and right limits. So this is kind of an extension of that. So I guess to begin, what's continuity? Well, continuity it relates to functions, and a function is said to be continuous if there are no breaks or holes in its graph. Most of the functions that we look at are continuous functions. However, many of the functions that are used in modeling real-life situations are discontinuous because of real-world limits that apply to the functions. There are generally two different ways that a function will be discontinuous. Either you'll run into some type of vertical asymptote, or the function's just going to jump from one point to another with something like a piecewise function. And remember from the very first lesson that the limit as x approaches c of f of x is only true if the limit as x approaches c from the left is equal to the limit of x approaching c from the right. And if those are different values, you get a different value coming from the left than you do from the right, then the function, or then the limit does not exist. Alright, so how do we prove that a function is continuous at a point? Well, we follow this rule here. For a function to be continuous at a point, the limit of the function as the graph approaches that point must exist and be equal to the evaluated value of the function at that given point, which must also exist. That was a very wordy explanation. But basically, there are three rules. 1, 2, 3. Alright, so first off, the limit must exist. The second rule is that the evaluated value at the point must exist, so f of c must exist. And then the third rule is that the limit must be equal to f of c. And if any of these things are not true, then the function is not continuous at that point. So let's move on to an example. Here we have a piecewise function, and it just says determine if the function is continuous at the given location. So I'm going to start by drawing a graph. You don't actually have to draw a graph if you don't want to, but I'm going to do it both algebraically and graphically for this example at least. So here's our basic graph, and when x is less than 2, y is equal to -1. So x is less than 2 here. So we draw an open circle there because it's going, it doesn't include that point, it's less than 2. And then we just have a line going straight back that away. Alright, and then when x is greater than or equal to 2, y is equal to 3. So at the point 2, it's equal to 3. We have a closed circle. And then we have a line going way off infinitely in that direction. Alright, so based on our knowledge, we can already tell that this limit coming from the right does not equal the limit coming from the left, and that violates our first rule that the limit must exist. So we can already tell that this is not continuous. But for the sake of showing you how to do this properly, let's just go through it and do the whole thing algebraically. Alright, so let's look at this out. We can see that the limit as x approaches 2 coming from the left, or then from the negative side, would obviously be -1. And the limit as x approaches 2, coming from the positive side, would be equal to 3. And finally, the evaluated value at that point, f of 2, would be equal to 3. So this rule is true. F of 2 does exist, but the limit does not exist. Therefore, this function is not continuous at x equals 2. Or we could just write a big no. Okie dokie. Next example. So first, we write the limit as x approaches 1 of the function f of x, and I'll just write f of x, we know what it is, and then we're going to get some value. And we have to evaluate it coming from the left, and then we have to do it as it's coming from the right. So coming from the left, we plug 1 in, we get 3 plus 2, that equals 5. Coming from the right, well, that's also going to be equal to 5, obviously. So our first rule is satisfied. The limit does exist, and it's equal to 5. Now we have to also prove that f of c, and in this case the c would be 1 because we're approaching the point 1, f of 1 has to also equal 5. Plug 1 in, 3 plus 2 is 5, so f of 1 equals 5. And now, as you can see, all three of our rules are satisfied. The limit exists, the function exists at that point, and because 5 equals 5, all three rules are satisfied. They're equal to one another. So f of x is continuous at x equals 1. Alright. Here's one more example. Removable discontinuity is what this one's called. This is another piecewise function, as you can see. So when x is less than 3, y is equal to 2. When x is greater than 3, y is equal to 2. So we'll have our graph here. So x in 1, 2, 3, 4. So 3 is there. So at the point 3, x is actually equal to 4, as the last rule says. So we'll put that point in there. Then at point 3, we'll leave an open circle, and then it just kind of goes off in both directions. And that is what that graph looks like, roughly. And this is called removable discontinuity. Sometimes it's called hiccup discontinuity, just because it kind of pops out of there. So if we evaluate this for the rules, the limit as x approaches 3 from the negative, and the limit as x approaches 3 from the positive or from the right direction. And we get them both equal to 2, because it's approaching 2 from each side, as you can see. But when we evaluate f of x, or f of 3 in this case, what do we get? Well, at the point 3, it's equal to 4. So even though the function exists and the limit exists, 2 is not equal to 4, and therefore this function is discontinuous at x equals 3. On to our final example. Look at the following graph. Note the vertical asymptote at x equals 0. Is this function continuous at x equals 0? Well, as you can see, there's a vertical asymptote going straight up there. And obviously it's not continuous because it can't jump from way down there to way up there. It just doesn't happen. Additionally, when we plug in 0 for x, we get the point 1 over 0. That's not a number. That would just come up as an error on your calculator. That does not exist. There is no y value at the point x equals 0. So f of 0 does not exist. The limit at the point 0, well, if you're coming from the left, this side, you can see how you're approaching negative infinity. But if you're coming from the right, going this way, you would see that you're approaching positive infinity. Positive infinity and negative infinity, the limit doesn't exist at the point 0. So in fact, all three rules are invalid. And therefore, there is no possible way for this function to be continuous at the point x equals 0. Alright, that wraps up this lesson. Join me in the next lesson. We're going to finally get on to derivatives. Fun stuff.